Welcome and thank you for attending this session about data virtualization, data lake using SQL Big Data Cluster. My name is Dennis Torres, I'm a Brazilian living in Malta, and I'll be delivering this session. Oh, what are you doing here? Well, I'm trying to deliver the session, and you, what are you doing here? Well, I'm trying to deliver the session. Let's do this. Since we are two, one of us will deliver the session and the other will be answering the questions on the chat during the session. So we can do both things at the same time, right? Okay. So I'll be answering the questions on the chat. Okay, so let's go to the chat. So let's start. Welcome and thank you for attending this session about data virtualization and data lake using SQL Big Data Clusters. My name is Dennis Torres. I'll talk about how to use this concept, what is data virtualization and how to use this concept using SQL Big Data Clusters. This is part of our learning path. This means that we have a sequence of many sessions, and if you are following the sequence, you end up with a very good knowledge about big data clusters. We are on the third session. First, let's talk a bit about PaaS. PaaS is about community, and it has many features to get you involved with community. Local groups, SQL Saturdays, virtual groups, and so on. So if you are not yet involved with PaaS, you should, because you will learn a lot and you make a lot of friends all around the world. It's great for professional network and learning. At the end of the session, you have a session evaluation. You can fill the session evaluation until Friday. We ask that please you fill the session evaluation. We would like to know what is good or not with the session so we can improve the session. That's me. Dennis Torres, I'm a Brazilian living in Malta. There are my contacts. Feel free to get in touch and connect. It will be a pleasure to connect. I'm a data platform MVP and trainer specialized in data platform. What we will see today. Let's review what's big data cluster, because we are already on the third session on the learning path. Let's talk about data lakehouse. What's a data lakehouse? How data lakehouse and big data clusters work together. How they work together. What's data virtualization? And data virtualization in big data cluster. Let's start with what's big data cluster. It's simple. You already saw many definitions on previous sessions. So, big data cluster is a SQL Server tool for a data lake house. This brings another question. What's a data lake house? What's a data lake house? We know data warehouses. We already know the data warehouses. They are very old in the market. Then the internet brought to us the big data, huge amount of data produced by internet users or IoT devices or so on. And the big data brought to us the data lake. Why? Because the amount of data we have with big data is so huge, we can't be moving this data around all the time. It's not possible. We can't do that. So we need to leave this data in a single place. That's what we call data lake. So in this relation, data lake and data warehouse are similar because both are storage. Data warehouse is a storage for structured data, although that's not totally true, but I will not go deeper on this subject. I wrote an article about this. You can read on the link. And data lake is for unstructured data. So many speakers already talk on this way, although it's not very precise. So data warehouse is for structured data and data lake is for unstructured data and big data. So what happened? What happened is that data lake and data warehouse decided to marry and went on a honeymoon. And after the honeymoon, we got the data lake house. What's the idea of the data lake house? The idea is to have a data lake and data house together, both together. And in this case, we need tools to enable us to work with a data lake house. Tools to enable us to deal with unstructured data in a data lake and structured data in a data warehouse, to deal with both together. That's a data lake house, and Microsoft has two tools to deal with a data lake house. Two tools. And one of the tools is what we are talking today on this learning path. It's the SQL Server Big Data Cluster. So, data lake house and the big data clusters, how they work together. You already saw this graphic before on previous sessions for sure. And this is the big data cluster, how it's organized, and how data lakehouse works on this over this. Simple. We have the data pool to host data houses. We have the storage pool to host data lakes. And we have the master instance to be the entrance point, the start point to reach this data, and the compute pool to break down processing over this data. So this is how the big data cluster works with a data lake house. Is this enough? Is this what we need to deal with a data lake house? And is this what the companies need? Not exactly. Let's imagine a company across the world, a big enterprise. It has a headquarters somewhere and many branches. One branch in Malta, one branch in Germany, one branch in the United States. What will happen? What is very common to happen is that each branch will start their own data architecture. So each branch has its way to deal with data. For example, it's possible that each branch has a data lake, or each branch has a data warehouse, or some branches may have both data lake and data warehouse. So each branch already has a data solution that fits on the needs of that branch, for that branch to make business. But the headquarters needs information about the business. It needs the information to analyze, to make business plans, and so on. It needs to analyze the information. How would we do that? One first thought would be, let's make ETL and import everything to the headquarters. No, it doesn't work. It doesn't work because we are already talking about big data. And big data is stored in a data lake intended to not be moved. So if these branches already have data lakes, the intention is to not move that data. It's a huge amount of data. The amount of work to move the data to another place would be too much, and we should not do that. So how do we solve the problem? Simple. Before going to the solution, let's imagine this problem from another point of view. Imagine that a manager approaches you and makes a request. Oh, we have an account on social media and we are collecting all the interactions with this account on social media. So I would like you to analyze these interactions, check if these interactions are positive or negative, and the feedback the customers are giving, and so on. All the tweets are stored in an ADFS storage. So this is a set of unstructured files, and I would like you to analyze this and give me some feedback about this information. But that's not only this, because we have a customer database which is stored in SQL Server. I would like you to mesh this information in a way that I would like to know if the customers who are having more interactions with our social account are the same customers that are buying the most products, the more expensive products, and so on. I would like to relate the interaction with our social account and our orders for the customers. So I would like this information, this interaction between a relational and a non-relational data. But there is still a third problem, because just a few months ago we acquired a new company and we are incorporating the data of that company. That company has their customer base in an Oracle, and they would like to include their customer base on this analysis as well. So you would need to join the information from the ATFS, from the Oracle, and from SQL Server, and give me this analysis. At this point, you are already thinking about ETL, SSIS. If you are more of a cloud person, you are thinking about Data Factory or something like that. Then the manager comes to the last request. The last request is, I need this for 1 hour because I will have a meeting in 1 hour. I need this information to show in the meeting. That's the moment when you got crazy. You go completely crazy. How will you achieve this in a single hour? It's not possible. Is it possible? Data virtualization to the rescue. How data virtualization can solve this problem? Simple. We already have the concept, the idea of a data lake, a place where all information is, and we don't move the information from the data lake. The idea of data virtualization is to create a virtual data lake, to create a main contact point where our applications will be able to connect and query a model that we will create without caring, without needing to care about where the information really is. If the information is local, if the information is in another branch, in another country, which format the information is, and so on. So we have a central point of connection, and this central point of connection maps many other points of connection. So that's the idea of a data virtualization platform. So it's not only about to support a data lake, but it's about to support a data lake of data lakes in a big enterprise. That's the point. And this will enable us to solve this problem with a single query. In an environment with data virtualization, we can make a single query over SQL Server, Oracle, ATFS, and solve the problem of the manager. That's it, in 1 hour or much less. How the data virtualization works with the SQL Big Data Cluster? Simple. We have two features inside the Big Data Cluster to work with data virtualization. You can think that, one of the features is for unstructured data and the other is for structured data. Not necessarily. The point is, we have two features. One of the features is called ATFS tiling. The ATFS tiling allows us to map to our ATFS storage external ATFS storage. So we can map external storage to our ATFS storage, making it appear to be local storage when in fact it's not local storage, but it will appear to be local storage. This one really is for unstructured data, but the other tool that we have is called external tables or external objects. It's made on the structured point of view, but we can point the external objects to any kind of external storage. It can be unstructured external storage or unstructured external storage. Both will work with no problem. So we have these two tools: external tables, external objects to connect to external elements. We have ATFS tiling that we can use on our storage level to mount remote storage. And a third feature is the push-down feature. What's the push-down feature? The push-down feature is the feature which allows the SQL Big Data cluster to send processing queries to the remote environment. Because our queries will have lots of predicates, group bys, aggregation functions, and so on. And the remote storage is not a storage. The remote data can be in an Oracle, for example, or a remote Spark, or something like that. So our SQL Big Data cluster will be completely able to send processing requests to the remote point. So to avoid to make all the processing in our SQL Big Data cluster, and it will avoid to move the data. So the remote responsible for the data will filter the data, process the data, and send to us exactly what we need to complete our request. How does this work? So we have a master node on the SQL Server Big Data cluster. Let's imagine that in Malta we have a data warehouse. This data warehouse is already built in Oracle or SQL Server. It's there, already built. We will not make an ETL to migrate this data. We will access that data warehouse. How? We will create in the master node external tables pointing to that external data warehouse. Then, many applications will be able to connect to the master node and query that external table. That's the external tables and the model that we will be creating inside the master node. And the master will decide if it will send the query directly to the external point, in this example, the Oracle in Malta, or if the master decides the work is too much, it can send the job to a compute pool inside the big data cluster, which will break down the tasks among many compute nodes, and each compute node will contact the external side and make part of the request. So the request will be broken down on a cluster. And that's how we solve this for a data warehouse. But what if on United States we have a Spark data lake? In this case, it's unstructured data, it's a data lake. Well, one solution for this is to link this external data with our storage pool. Then we can use our other tool, our second tool, ATFS tiling. We use ATFS tiling to map the external data lake environment to our ATFS storage. And if the master node wants to access our ATFS storage, it will access our ATFS storage through the compute pool. And that's the interesting part, how the master node will access unstructured storage. That's the point. The master node is our central virtualization point, is our virtual point of entrance. So in the master node, we will create external tables pointing to the big data cluster storage as well. So we'll have external tables pointing to that ATFS storage. And in this case, when pointing directly to the ATFS storage, the master node will use the compute pool, and I will prove that on the demonstration later. It will use the compute pool. But not only that, because inside the storage pool, we also have a Hadoop. So the master node can choose to send a job to the Hadoop, and it will be the task of the Hadoop to break the job among many servers inside the storage pool and access the data, retrieve the data from the ATFS storage. So we have two paths to access our data. Both paths end up on the external tables, making a single entrance point for any application who wants to query our data. The master node becomes a single entrance point for any application. There are other possibilities. For example, we have here Germany and England. The other possibilities would be if we have production data, maybe structured or unstructured. These branches don't have either a data lake or a data warehouse. They have production data. How do we deal with that? We would need to take a decision. Would we create the data warehouse or the data lake in the branch and then virtualize? Or would we create the data warehouse or the data lake already inside the big data cluster on the headquarters? It's a decision that we need to make, and both situations are possible. If we will create this inside the SQL big data cluster, we will store the data warehouse on the data pool and the data lake on the ATFS storage. But this will be more covered by other sessions on this learning path, which will talk specifically about the data pool and the storage. I will focus more about the data virtualization part. So let's see a demonstration, and on our demonstration, we will see how to virtualize a SQL data warehouse, a remote SQL data warehouse, and how to virtualize a remote ATFS data lake. Let's start our first demonstration showing how to virtualize a remote data warehouse. I have AdventWorks DW. This is my remote data warehouse with many dimensions and fact tables. And I have my big data cluster. So let's start. I will first create a database inside my big data cluster. So AdvWorks DW. This database will host my DW virtualization. That's great. The database is here. Now, in order to have access to the remote data warehouse, I need to create the credential I use to log in to the remote data warehouse. I use database scoped credentials. Maybe you would like to read a bit more about how credentials work in SQL Server. I created the credentials, and this is the scenario that we are building. I have a remote data warehouse. On this image, the data warehouse appears as Oracle. Mine is a SQL Server, Azure SQL DB, in fact, but it will be the same. And I'll create the external tables in the master node, and let's analyze how the master node will call the compute node or call directly the remote data warehouse. First, I need to create the data source pointing to my remote data warehouse. Here is the creation of the data source, specifying location, the credential I already created, and enabling push down. So every time my big data cluster would like, it can push down a query directly to the remote data source. Maybe you'd like to read more about the syntax of the location. There are many variations on the syntax of this location. Let's execute, and my external data source is created. I can check here in external resources, external data sources, and here it is, Adventure Virtual. My external data source is created. Let's create external tables. I'm creating the fact internet sales, it's a fact table, the DIN customer, and the fact product inventory. I'm creating two fact tables and one dimension table. I'm creating all this for the example. There are differences on the fact internet sales and fact product inventory that will create some difference on the result of the queries. The external tables specify the location and the data source. Location is basically the database, the owner of the schema, and the table itself. Let's execute, creating the external tables, and the external tables will appear on tables here. Here are the three external tables I just created. That's it. Before making any query over this environment, I would like to analyze if the pushdown will really happen, how the pushdown will happen, and so on. So I will use extended events on my remote data warehouse to analyze the results of the pushdown. I have another notebook here prepared to create the extended events. On Azure SQL DB, it has some difference from the on-premise environment. Maybe you'd like to read a bit about extended events on the Azure SQL DB. I need to establish credentials to store the files of the extended events on a storage account, Azure storage account. And then I create the event session. I'm using the RPC event started and completed, and the SQL statement event is started and completed. And I'm creating and already starting the extended event. I will create the extended event session. The session is created. I can see the session on SSMS. Here it is. The extended event session is created. So I'll be able to check the queries sent to the data warehouse, to the remote data warehouse. Let's get back to our example. Before execute the first sample queries, let's make another example of an external table. I created already 3 external tables. That's good, interesting. But there is another way to create these external tables. I can get my big data cluster, right click, select manage, and I see the managing dashboard of the big data cluster. Here I can choose the button virtualize data. It opens the virtualization wizard, and I can choose where will I virtualize the data. My external table will be created on ADVWorks.dw. Next, what data source will I use? I already have the data source created. It got the server name. The database is Adventure Works DW 2016. Next, then I can choose the tables, and let's get DIN products and DIN geography. So it will create these 2 external tables for me, DIN products and DIN geography. It's suggesting the name, it will be a similar name. Okay, next. And I can create or generate the script. Let's ask to create. And here I have two additional external tables, the in geography and the in product, created using the virtualized data wizard. Let's get back to our script. Let's execute the query over the fact internet sales table. We have here a simple count over the fact internet sales. For me as a user, a consumer of this query, it doesn't mind where the table is, but we know this table is on the remote data warehouse in a different branch, can be in a different country of this company. So we have the total here. Let's analyze a bit of the internals of this query. We need to identify some details about this query. What do we need to identify? First, did this query use the compute pool or did not use the compute pool? And did the push down happen or not? Let's analyze. First, I use a DMV to check the compute pools, the existing compute pools in this environment. I use the sysdm exec compute pools. So I will execute. And here we can notice we have two compute pools. That's not true, not true at all. We have one compute pool. But the master node is also considered a compute pool. So the master node appears as a compute pool 0. And the other compute pool appears as a compute pool 1. But the master is a single node, while the other compute pool can have many compute nodes. Every compute pool, and in this case it includes the master node, has a head and many computes. The same node can be a head and compute at the same time. But other nodes on the compute pool would be only compute, not head. The head controls the distribution of the process among the compute pools, the other compute nodes. So, in my example, in this big data cluster sample, we have only a single node inside our compute pool, the compute pool 1. Only a single node, and this single node is head and compute at the same time. While the master is also saw as a compute pool and is also head and compute at the same time. To further analyze this query, we need to discover the execution ID of this query. Again, I use some DMVs. This time I use the DMV exec distributed requests. So, distributed requests, and let's check the queries, and I have here the select count, and the ID of the query is QID 781. Now I use this ID 781 to get more details about the execution of this query. So I use the exec distributed request before. Now I use the distributed request steps to identify the steps of this execution. So let's check the steps. And here I can notice many details. Operation type, the type of operation that was executed, distribution type, location type. The location type is very interesting because it's telling us what was executed at the head, what was executed at a compute node, or what was executed by the DMS. DMS is Data Movement Service. It's a poly-based service. Poly-based is a feature which was created since SQL Server 2016 and allow us to access many different external sources. Polybase is directly linked to the external objects, to the external tables. So these tasks were executed by Polybase. Checking the commands, we can easily note how this was executed. They had created an ID, and this ID was used to create a temp table. The DMS went to the external source to retrieve the information, and after the information were retrieved, the temp table was dropped. And we can note the compute pool ID 0. This means that this query that I made over fact internet sales was not sent to the compute pool. The master pool believed it was able to execute this query alone without using the compute pool. The master node did everything. Let's go ahead, and after checking the steps, I can check what happened inside Polybase. I can check the DMS steps and what happened inside Polybase. So this step is step 2 of the DMS. So I use another DMV, DMSX DMS workers to check what happened inside Polybase. Let's execute. And here we have 16 records. This is a very important number for us, 16 records. Why this is an important number for us? Because the machine I used to provision this cluster has 8 cores. This means that the number of records is the double of the number of cores. But why the double? Because I have 2 types. I have first the external reader, exactly 8, exactly the number of cores, and then the writer, which are also 8, the exactly number of cores. So I have 2 types of tasks, external reader and writer, which were broke down among the cores of our machine. The compute pool ID is still 0. It was executed using the master node. And I have here the query time. It's interesting to note on the external reader that the query time, only one of the readers has a valid query time. All other readers are 0. This means that it broke down the execution among 8 cores. But only one core had something to do. The other cores did nothing. They had no work to do. Only one of the cores really did something. Okay, this is what happened inside the step 2, which is the first Polybase step, first the data movement step. Let's check what happened inside the step 3, the second Polybase step. On step 3, I have only 2 tasks on step 3, a direct reader and writer. Basically, it reads the result and returns the result to the master node. This query was executed on the master node without using the compute pool. This we already know. But was the push down executed? Let's check our extended events to see if the push down was executed. I can make a query over the extended events. I'm executing the query over the extended events. So I have here 10 resulting rows, and we can note many details about these rows. The query over the extended events is here. It's important to note many rows are duplicated because I'm capturing the starting and completed event, so the rows are duplicated. And I have here a query to retrieve the information about the columns of the table. So the big data cluster retrieved the information about the columns, retrieved information about partitions, and then took the decision to make the push down, sending the count to the destination server. In this case, it's making a group by and making a count big. Group by and count big, sending this to the destination server, to the remote data warehouse server. So the push down was done. The details about the query was sent to be processed by the remote data warehouse server and not at the big data cluster. And that's very interesting. That's very good. Now, let's go further and make another query. Now I'm making a query over the fact product inventory. What's different on this query? The difference on this query is related to the destination. I, as a user, don't need to know that. But the fact product inventory is partitioned on the data warehouse, on the remote data warehouse. And that's very interesting because it's very common that a data warehouse table will be partitioned. That's very common. But let's see how the big data cluster reacts when the target table is partitioned. So I will execute the query. Once again, it's bringing me the data from the remote data warehouse, another country, who knows. So I have the total here. And let's analyze how this query is working. First, I need to discover the ID of the query exactly as before. So the ID of the query is 802. Now I use this ID to check the further details about this query execution. Let's check the steps of the execution. Here I can see the steps of the execution, very similar as before. There is not many difference here. It's the same, and it's still using the master node as compute pool. No difference. But let's go deeper. Let's go to the DMS steps. Let's check the detailed steps about this execution, 802. And again, I have 16 rows. Once again, I have external readers and writers. That's very interesting. It's the same, but this time, the external readers really had some tasks to do. Take a look. The external readers really returned rows. I really have returned rows here. That's interesting. Last time it was only a single reader which returned row. And step 3 will be very similar to the previous one. Let's check the extended event. So I will check the second extended events query. I'm executing the extended events query. "18 rows, and mind the number of selects. Of course, they are double, they are duplicated because I have starting and completed. So I have a total of 12 lines. So I have 6 selects executed, and the point is, mind the query. Each query is selecting from a different partition. What this means? This means that the big data cluster was able to identify that the remote table was partitioned and used this on his advantage. It made the query, it broke the query for each partition in order to have a faster result. That's it. Of course, this kind of behavior will change according the destination, the target destination. It will be different depending on the target destination. Now, let's go to our third query. I will again execute a query over fact product inventory. But this time I'm using the option force scale out execution. This query hint will make a change on the execution of the query. Let's execute. Again, it's getting the remote total for me and bringing it to me, and I don't need to have any idea where it is. Now I will check the query ID, the ID of this execution. The ID of this execution is now 692. I will use this ID 692 to get further details about the execution one more time. So let's go to the distributed request steps, the steps of the 692 execution. And here the steps are not exactly the same now, because this time I have a single DMS step and more compute steps. And the main difference, the compute pool ID now is 1. That's the difference. That query hint made the difference and sent the query to be broken down by our compute pool instead of the master node. Instead of being executed on the master node, the query was sent by the compute pool. So what this means? Do we always need that query hint to make a query being processed by the compute pool? No, we don't. There are many different rules which set if the master node will send the query to the compute pool or not. And this depends also on the target. In this situation, the target was SQL. And the two rules about a query to a SQL target are: the destination table needs to be partitioned, and we need to use the query hint. For SQL targets, we need to use the query hint. Now, let's analyze the DMS step, the single DMS step we have. Again, 16 rows. And again, we have many external readers and writers, 8 external readers and 8 writers. And again, the external readers really did some tasks in the processing, especially because now they are processing, each one is processing a different partition. Each one is processing a different partition, but the process now is happening inside the compute pool. I can analyze what happened in the compute pool as well. There is another DMV that we haven't used before, is the DMExec distributed SQL requests. This DMV allows us to check what happened inside the compute pool. So now I'm getting the step 3, which is the compute step, in this case the return operation, to check what happened inside the compute pool. Let's execute. And we can note it's a single SQL task, but with a long SQL statement. A quite long SQL statement, make a long select to join the results. This select is joining the results and returning back the result from the compute pool. Let's check here some practical result from this. The point is that in the headquarters of the company, and this headquarters may be on Brazil, for example, let's imagine the headquarters is on Brazil, I'll be able to make a query and get information from the data warehouse located in Malta. So I can select the total fact internet sales for a year from the data warehouse hosted in Malta. And I have here the results. And the Azure Data Studio allow me to check these results in a very good way. I can make a chart and configure the chart to show me in vertical direction. So now I have the amount of sales by year that are registered on the data warehouse from Malta. So this is an example of a virtualization of a remote data warehouse. I virtualized many tables from the remote data warehouse, and now I can access the information from this data warehouse connection to my master of the SQL Big Data Cluster. And I don't need to know where this data warehouse is. I have no need to know about. Now it's my turn to make the demonstration. I know I'm 1 year delayed with this cert, but let's say it's for good luck. So I will select the database, I'll create a schema for the new tables that we will create, and this demonstration will be about virtualizing a data lake. So the idea is that we have a remote data lake, like the example you saw on the PowerPoint, and we will use HDFS tiling to virtualize the data lake. As you can see on this image, the master node can access the HDFS using the HDFS storage directly or using Hadoop. There are two options to access the storage pool, HDFS directly or Hadoop. And when using HDFS, it uses the compute pool. When using Hadoop, it goes directly from the master node. We will see all these details on the demonstration. First, I'll create the data source. These are very special data source because they cover exactly what I showed on the image above. These data sources are needed to make the link between the master node and the storage pool. One of the data sources to make the link directly to the storage pool, and one data source to make the link with Hadoop. So what will define if the master will use the storage pool or the Hadoop? Our choice. We will create external tables over one data source or the other. We will choose which external tables we will create over one data source or over the other data source. It's the choice. And so we have here the HDFS environment. Our SQL Big Data has the HDFS environment, but only the full folders. I don't have any data on the HDFS. I could insert some data there, no problem. But in this case, I will mount the remote folders using HDFS tiling. I will mount the remote folders here. And there are 3 different ways to mount the remote folders. Let's start. First, I can use a Python notebook, a Python 3 notebook to mount the remote folders. I'm saying that it's a Python 3, it's a Python 3, but most of the statements are in fact command line statements. We are using the exclamation in Python to run command line statements. So most of the statements are command line statements. And here on the first set of statements that define mount credentials, the credentials for the remote mount, and the password for the cluster. This execution doesn't give us any result, it's only setting environment variables. And now I use the AZ data to make a login to the cluster using the environment variables that I just set. So I'm logged in to the cluster, and I use again the AZ data, this time to mount the remote path, ATFS mount create. I point to the remote path, I mount the holidays folder as a local holiday folder in my ATFS. Let's execute. Okay. And now I will check the status of the mount. The mount is an asynchronous call. So the statement calls the mount and returns. So to know if the mount was correct made, I need to execute the check for the status of the mount. And here the status and the mount is ready. I can make a refresh on the ATFS and the mount is here, holidays. Let's get back to our first demonstration. Now let's check the second method used to mount the holidays. I will right-click the ATFS and select Mount on Azure Data Studio. So I can use the Mount window, specify the remote URI, the name of this mount, let's call New York Taxi. I could put some credentials, but I don't need because this is a public storage kept by Microsoft. I don't need credentials for this one. And I'll click OK. And that's it, another refresh. And I have my second mount. Now for the third mount, I will use the command prompt. I really use the command prompt, and you will notice it's very similar to the Python notebook. But I just need to put directly the statements on the command prompt. I'll set an environment variable. An environment variable containing the credential for the remote mount, and so I'll use this statement to define the mount. It's done. Let's check the status. And my third mount is done perfectly. Let's get back to our script. But how can I identify which folders here are mounts and which folders are local folders? The problem is that at the moment that I made the mount, that I made the connection with the remote folder, the Azure Data Studio doesn't update the status here. It's a visual bug. Let's close Azure Data Studio and open it again. So magically Azure Data Studio is opened again, and now you can notice the difference between the mounts and the regular folders. The mounts have a link in the icon. The regular folders don't have this link in the icon. And in our example, each mount has a different file format. For example, New York Taxi has a TXT compressed. Holidays has a Parquet file. This is a Parquet file. also compressed and whether has a CSV file. So we are talking about a data lake, unstructured data types. And these three mounts could be coming from different places in the world, different branches of the company, and so on. And as a user, I don't care. In order to deal with these different data types, I need to define some objects. They are called external file formats. I will define an external file format for the Parquet, specifying the compression which is being used. An external file format for CSV, and an external file format for the compressed CSV, also specifying the compression being used. Let's execute. Now the three file formats are already created. I can check the database, Adventure Works DW, external resource, external file formats, and here they are. The three file formats I just created. Before going ahead with the queries, let's see other ways how Azure Data Studio helps us to deal with the ADFS. First, let's take a look on the weather, especially because weather is CSV. Azure Data Studio is very prepared to deal with CSV, not so much with other formats. SQL Big Data deal with all these formats, but not the UI, not the Azure Data Studio. So what I will do here? First, I have the option to visualize data from CSV files. This is one of the options that I have when I right-click the folder. And if I right-click directly the file, I have one second option, Analyze in Notebook. Let's try doing this first. It opens to me a notebook. This notebook is using PySpark. So it's basically Python Spark, and it's reading the data of the file and showing the first 10 rows. Let's execute. So it started a Spark session, and now I see the 10 rows as the result. It's a CSV. I have not selected any column or any detail specifically, so it's not very easy to read. But the fact is I can use a Python notebook to work with the data on my ADFS environment using my SQL Big Data cluster. That's very interesting. The other option, the option of visualize data from CSV files, it's a wizard to create an external table pointing to those CSV files. Mind that this is different than the Data Virtualization wizard. The Data Virtualization wizard doesn't even work for these files. Mind, the external tables work, no problem, but the Data Virtualization wizard are made to really external files, not files in the DFS storage pool. While this second wizard can map CSV files on the storage pool to external tables. So it's proposing the creation of an external table of file format. I can click next. It shows me the data, it's identifying the data, but since it's a CSV, the columns don't have a name. There is no name for the columns. I can click next. I can put a name for the columns here. I would need to identify one by one. then click next, and here I can visualize data or generate script. Virtualize data, the option virtualize data will create the external table. Generate script will generate the script for me to create the external table. Then if I close the wizard, I need to click that close and click in cancel. Then closing the wizard, I have here a file with the script to create the external table. Let's get back to our example script. Let's go ahead on it and create our external tables, already planned external tables, first on the storage pool. What this means, I'm using as data source the SQL storage pool. This means that SQL Server will go directly to the ATFS environment to read the data. And this example is with the weather table, so it's using CSV format. Let's create this table. And table created. Now I will execute a simple select top 100 from external table weather. So it will bring to me 100 rows from the weather external table, which is in fact the CSV file on our ATFS environment. So 100 rows here. Let's check some internal details about this query execution so we can know if the compute pool is being used and how the query is being executed. The process is quite the same than the previous demonstrations. First, I need to find the ID of the query. Here, my query has the ID 766. Now I'll go in details about the steps of this query. Let's check the steps this query has. 17 steps. The interesting part is the use of the compute pool for most of the steps. Most of the steps use the compute pools, except some which were returns to the master node. Here it is. And we can note the use of temporary tables. It uses temporary tables to move the data among the nodes. That's very interesting. We have the DMS steps here in the middle, and we can check more details about the DMS steps. The DMS step ID is 7. Let's check the details. And 16 steps. It's exactly the same as before, no difference. There are differences on the source info, destination info, but it's exactly the 16 steps. 2 sets of 8 steps because the machine has 8 cores. That is it. It's using the compute pool. What this means? This means that when we make a query over an external table that goes directly to the ATFS storage, it will use the compute pool. That's it. Always, this is one rule. SQL Big Data use the compute pool to go directly to the storage. Let's now create our second table. This time, this table is over the Hadoop data source. So it will access the data through Hadoop and not directly through the storage. Let's create the table. It's done. Execute the query, retrieving 100 rows. So here we have our result, the query result with 100 rows. And now let's again check the internals. I first need to discover the ID of the query. And here it is, 977 is the ID of the query. Let's use this ID to check the steps of the query. 12 steps, exactly as before. But this time there are some difference. One of the difference, it's using compute pool ID 0. This means that it's using the master node. Every time we make a query over an external table going to Hadoop, the master node will go directly to Hadoop. We will not break down the query among the compute nodes. Why? Because it can push down the work to Hadoop directly. If the master node needs to go to the storage, it can't push down too much to the storage, so it breaks down on compute nodes. If it's going to Hadoop, it goes directly to Hadoop and pushes down to Hadoop. And we have here a Hadoop round-robin operation. It's a different operation. We haven't saw this before. And we can go in details about this step 7. Let's execute the query, retrieving the steps. Again, we have many steps, the external readers, the writer, and we have some additional steps, round-robin converter. But what most calls the attention, our attention here, what most catches our attention here, is the step cancel. This means these steps were not finished, they were cancelled. Why? Because we are reading only around 100 rows. Only 100 rows. It's not too much. So it doesn't justify these steps. So in fact, with what Hadoop did, it was replace this step, Hadoop round-robin operation, with the following one. Let's try this step 8. And you can see parallel copy reader being executed to transfer the data. And what we discover with these internals, we discover that when the master node is making access to external table directly to the storage, it breaks down the process to the compute nodes. When it's making access to an external table linked to Hadoop, it sends the execution directly to Hadoop. And Hadoop is able to identify if the amount of records and the amount of work really needs to be executed there, or he can replace the steps with a parallel copy reader or something more simple. So without these details, let's create our third external table. It's the holidays table. And here we retrieve the 100 rows from the holidays table. 3 external tables created, 2 over the SQL storage pool and 1 over Hadoop. Now, let's make some more interesting results. Let's get some more interesting results. I'm on a different notebook, so I need to make use of the database. Yes, done. Now I use the trip external table to make a calculation of the total of trips according the passenger count for each trip. the number of trips which had only a single passenger, number of trips with 2 passengers, and so on. Let's execute this query. So this query took 11 minutes on my demo BDC, the fastest 11 minutes you ever saw, but brought us the result, the total of trips according to the number of passengers. We can build a graphic with this. This is an Azure Data Studio feature, not related exactly to BDC, just a Data Studio feature. So we can see exactly the number of trips according to the number of passengers. Then the next query, I will read from fact internet sales and group the information by year, checking the total of orders by year. Let's execute it. And here again, I have the total of sales by year. Let's make a graphic with this information. Configure the chart. Vertical. Close. So it's easy to see that 2013 was the best year for the company, for sure. And now let's make a query to get the information by day, by each day, each date, only for the year 2013, which was the best for the company. And again, let's see a graphic. I need to configure the chart. Vertical. And we can use this chart to check the amount of sales by day. And we can clearly see some days where the sales dropped a lot. We had some huge drop on sales. That's interesting. Let's try to discover why we had this drop on sales. We have the information about holidays. We got the information about the holidays. So I will use this query over fact internet sales. Mind that fact internet sales is a table from previous demonstrations. A table virtualizes from the data warehouse. And I read information from the holidays, which is a table virtualized from the data lake. So I'm making the query on both tables together and making a left outer join between them to mix the sales date with the holiday date. And I'm making some adjustments on the columns just for the graphic, just to ensure the graphic will show correctly. So for the field holiday, if the holiday is null, I transform in 0. If it's not, I make the same value as the total, so the graphic will show correctly. Let's execute this query. I already see the result. And let's build the graphic. Vertical. Close. So we can make some interesting analysis on this graphic. We can see the daily sales, and we can see in pink the days of holidays. It's interesting, the days of holidays have a quite big amount of sales, but not the biggest. Usually some days after the holidays have even bigger sales than the holiday itself, except on the holidays on the starting of the year, when the sales drop a lot. It's a very interesting analysis, and the most interesting part of this analysis is that I'm using our virtual data lakehouse. Using the SQL Big Data as a virtual data lakehouse, I'm reading information from a remote data warehouse that may be in another country, a remote data lake that may be in a different country, merging this information and making the analysis. That's the idea of data virtualization.